turning on the recording.
So thank you, but okay. Anyway,
It should be recorded now, I think.
oh, thank you very much, Maurice. Thank you. Okay, can you see the whiteboard?
Yeah, now it's perfect. Everything is perfect.
Yes.
It's perfect. Okay. Okay, let's begin. So, at the lecture, we considered sets, and we did it from the so-called axiomatic point of view. So we don't want to define set, for it seems to be impossible, as set is the basic, a primitive notion, but rather we want to codify the behavior of sets. Namely, we say that one set might be an element of another one. What is the main idea of this relation? One set is an element of another one. Say this is in fact a rectification of our natural language word is. A is B. What doesn't mean? In general, we have at least two distinct meanings. At least two distinct meanings. First, you may say that 2 is even. 2 is even. And then you may say that a multiple of 4 is even. Don't you agree that the meanings of these two statements are principally different? The meanings of these two statements are principally different. Don't you think so? And if you do, then please clarify why. Why these two meanings are different? Any ideas, dear students?
Because the first one says that 2 is belong to set of even numbers.
So this is about an individual. This is about an individual. And this is about a class. What does it mean? Here we mean that every multiple of 4 is even. So these are two distinct meanings. Say you may say that I don't know. I don't know. Mickey is a mouse. Mickey is a mouse. This is about an individual. Or you may say that a mouse is an animal. This is about individual, and this one is about a class. Do you see the difference?
Yes.
And basically in mathematics, we want to catch this difference. Why is the distinction between elementhood, being an element, and being a subset? This one does not mean that a mouse, that means that means the mouse kind. the set, the class of all mice. So in mathematics, we want to catch this distinction via this one. And we say that the second relation, in fact, might be expressed in terms of the first one. We say that one set is a subset of the other one, of B, if and only if each element of A is also an element of B. So this is, by definition, and A being an element of B, this is a primary notion, a primitive notion. It is not to be defined. Is it clear? At least partially. Dear students, please give me some feedback.
Yes.
Okay. So you don't want to define what does it mean A is an element of B. In general, intuitively, that means that some individual A is a member of class B. But these individuals are also sets. Everything is a set. Everything is a set, so one set might be an element of another one. But this has, in general, nothing to do with this relation, where every element of A is an element of B. We don't say we don't say anything about A as a whole. We are talking about its elements. Okay. Now, let's recall another definition. When two sets are defined as equal. When two sets are equal. So please. If and only if.
Maybe when every element from X, every X which belongs to A belongs to B, and the opposite one when every X belongs
And
to
vice
B.
versa, of course, of course. By the way, we see that this one is similar to this one, but it is symmetric. It is symmetric, so we have the following statement. The following easy statement. A equals B when? If and only if.
A is a subset of B and B is a subset of A.
Mm-hmm. And now let's do the following. Let's prove formally that if A is a subset of B and B equals C, then A is a subset of C. How is it possible to do so? Let's prove it formally.
We can use the definition of equal sets, maybe.
Of equal sets and of set inclusion, of course. So, what do I need? I need to prove that for every X, if X is an element of A, then X is an element of C. How is it possible to prove such an implication under universal quantification? I say that, okay, let's consider an arbitrary X. If X is not an element of A, then of course the implication is true. So assume that X is an element of A. Our standard, our usual technique of proving implications. We assume that the assumption is true, and I want to prove then that the conclusion is true as well. How is possible to do so? X is an element of A, but we know that A is a subset of B. That is, every element of A is also an element of B. What does it mean? Dear students, please be active. X is an element of A. Every element of A is an element of B. What can we conclude?
Every element of A is element of C.
No.
Well,
It's
that,
given that
X
X is
belongs.
an element of A.
Yes,
Every
that
element
means
of A is an element of B.
that means X is an element of B.
Of course, of course.
And
But
from
also I know
equals C.
that every element of B is an element of C and vice versa. So X is an element of B, hence, by the second assumption,
X is an element of C.
the thing I need. Is it clear?
Yes.
But there is another way, which is in general better. Let's recall the statements we have proved about set equality and set inclusion. We already know that two sets are equal if and only if each one is a subset of the other. So, but what can you say about set inclusion? What if A is an element of B and A is a subset of B and B is a subset of C? Then
A is a subset of C.
A is a subset of C. So from these two, we may then conclude the following. If A is a subset of B and B equals C, then we may conclude that A is still a subset of B and B is a subset of C. Why? From this one. And as A is a subset of B and B is a subset of C, then according to the second statement, A is a subset of C. Here, I didn't mention any elements of A, B, or C. Is it clear?
Yes, it's clear.
Now let's formally prove that set inclusion and elementhood are distinct, and in general, it's possible to have any relationship between them. First of all, let's recall what the empty set is. The empty set, by definition, is the set of all natural numbers which satisfy some contradictory condition. Natural numbers which don't equal themselves. So, first of all, what is the main property of the empty set? The empty set, what are the elements of the empty set?
The empty set.
So you say that the empty set belongs to the empty set.
The
Yeah,
empty set
as-
is a part of empty set.
Empty set is a part of every set.
What does it mean, the part? What does it mean, the part of?
It's the subset of every set.
Here lies a problem. In mathematics, we want to make a distinction between being a member and being a subset, because these are distinct. These are distinct. Empty set, the empty set has no element. This is the main property of it. No X is an element of the empty set. No x is an element of the empty set, but we know that for each x, the empty set is a subset of x. Why is it so? What does it mean? It means that for each x, for each y, if y is an element of the empty set, then y must be an element of x. Is it true or false? This implication. What do you think?
It's true.
Why?
Because the assumption is false.
It's false.
Of course, the assumption is false. As the assumption is false, the whole thing is true. This implication is true. So, empty set is a subset of every set, but it has no element. By the way, do you remember another way to construct a new set? For example, if you have some particular set, say A, B, and C, you may group them together and obtain this set, which has the following property. What are the elements of this set? When X is an element of this set ABC?
When X is either A or B or C.
Of course. Of course. So, this set has exactly the elements A, B, and C, and nothing else. By the way, what if you take just one set, say A, when X is an element of this set?
When X is equal to A.
By the way, how did we call this set?
Singleton
Or what?
of set.
Which
Okay.
one? The singleton of A. The singleton of A. Okay. Is it clear?
Yes.
And now let's give some examples. We need A and B with the following properties. A, okay. A and B with the following properties. A does not belong to B. Neither A is a subset, nor A is a subset of B. A does not belong to B, but A is a subset of B. A is an element of B. It does belong, but it is not a subset. And the last one is when A is an element of B and also A is a subset of B. Can you please provide these examples?
Okay, well, the first one is A is like 1, 2, 3, and B is 3, 4, 5.
1, 2, 3, and 3, 4, 5.
Oh, wait, no. 4, 5, 6.
4, 5, 6. But why this set is not an element of B? Can you prove it?
Because elements of B are 5, 6, 5, 4, and 6.
And what of it? What if
and-
say 1, 2, 3 equals 4? Can you refute it? Why not?
I don't know.
So, probably you can't refute it. And if you can't, so this example is not very good. Okay. Let's take something else. By the way, the main idea of constructing such examples is that you take sets whose elements are known to you. Which are such sets? You know that the empty set has no element. And for example, the singleton of the empty set has which elements? When X is an element of this singleton, X is an element of this singleton. When?
When X is an empty set.
So this set has the only element, the empty set. And now look at this part. I need that that A is not an element of B. Which set has no element?
Empty
Which
set?
set? The empty set, of course. So I may take the empty set as B. And now I only need to construct a set which is not a subset of B. Which subsets the empty set has?
No subset.
No, you are not quite right. The empty set is a subset of every set. In particular, the empty set is a subset of itself. Of course. Every element, every present king of France is a present king of England. Well, okay. Of Germany, of course. But of England as well. For the empty set is a subset of any set, be it empty or not. Is it clear?
Yes.
So you need here as A, you have to take a set which is not empty. Which is the simplest non-empty set? The most simple.
One? I don't know.
Which one? One? This one. But why isn't it empty? Can you prove it? Use sets whose inner structure is known to you.
Oh, the singleton of an empty set.
Of course. Clearly, this is not an element of the empty set. Why? Because the empty set is, after all, empty. It has no element. Why isn't it a subset? Assume that it is. And now let's get a contradiction. Here, it said that the singleton of the empty set is a subset of the empty set. That means that every element of this set is an element of the empty set. Do you know any elements of the singleton?
The empty set.
Of course. So this statement means that the empty set is an element of the empty set. Is it true or false?
It's false.
That's false. So we have got a contradiction. If from some statement we have got a contradiction, that is a false statement, then the statement itself was false. So that's false. So please, now give an example of sets A and B so that A is not an element of B, but it is a subset of B. Can you reuse the empty set, say?
Well, maybe we can say that A and B are both empty sets.
Of course. Of course. A is not an element of the empty set as nothing is such an element. But the empty set is a subset of any set and also of itself. Is it clear?
Yeah.
Okay. What's next? And now let A be an element. Let A be an element of B, but not a subset thereof. That means that there should be some element in A which is not an element of B. So B, of course, cannot be empty. Why? As it should has at least one element. And A cannot be empty as well. As empty set, the empty set is a subset of every set. But here we need it not to be an element, to be a subset. So please, any ideas? Any ideas, dear students? Please be active. Dear students, are you here?
Okay, maybe we can say that B is the set that contains the singleton of an empty set and the I don't know. But no, this doesn't work.
Surely it will work. Why?
Why? But
Clearly, this singleton is an element of this set. Is it clear?
yes, but isn't A a subset of B?
No, no. Let's prove it. If it is a subset, then every element of this set should be an element of this one. The empty set is an element of this set. Don't you agree?
Okay.
Then this empty set must be an element of this one. But the only element of this singleton is what? Is our set itself. So if the empty set is an element of this singleton, that means that the empty set equals this set. But it is not possible. Why? One is empty while the other one is not. So this set has the empty set as an element, and if they are equal, then the empty set must be an element of the empty set, which is not true. Hence, this assumption is false. Any questions?
No.
Okay, let's repeat. Being a subset means that every element of A is an element of B. The only element of A is the empty set. But the empty set is not an element of this set. It is an element of its element. But it is not an element of the set itself. You know, the old feudal law. My vessel's vessel is not my vessel. Have you heard about it?
Yes.
The element of my element is not necessarily my element. Okay. And the last example, which is quite simple, quite easy, in fact, to obtain. How is it possible to make B both contain A as an element and have it as a subset? That means that B must contain both A and every element of A. How is it possible to secure it?
We can make B a set that contains the singleton of an empty set and the empty set.
Of course.
Yeah.
And A is what?
Is just the singleton of an empty set.
This most true. Clearly, this set is an element of our set, and also it is a subset. Why? The only element of A is an element of B as well. Is it clear?
Yes, but is it possible that A equal to empty set?
Here,
Yes.
of course, there is another example. The empty set is a subset of any set. So the only thing that remains that our empty set must be an element of something. Let's take the singleton. So this example is, of course, better as it is simpler. Any more questions or ideas? So what is the philosophical significance of this result? That means that neither elementhood implies inclusion, nor vice versa. It doesn't imply inclusion, nor it prevents inclusion. Is it clear?
Could you repeat this again?
From A being an element of B, it doesn't follow that A is not a subset. It may be a subset, it may not be a subset.
Okay.
Okay.
The negation of inclusion does not follow from being an element. Okay. So the main idea here is to take all these notions formally and using axioms and definitions. By the way, which axioms did we consider? Please list them. Name these axioms. We introduced which axiom? Do you remember the axiom of foundation, by the way?
Yeah.
What does it say?
That there is no infinite sequence of the elements in some set.
What does it mean, sequence of the elements? It is not possible to take an infinitely decreasing sequence of such form. where x1 is an element of x0, but it has x2 as an element, which has x3 as an element, and so on. It is not possible to infinitely descend into the structure of our set. So this is impossible. This is impossible. Is it clear?
Yes.
As a simple corollary, we have that there is no x which is an element of itself. Why is it so? For otherwise, if we have such x, then x is an element of x, which is an element of x, and so on. Is it clear? You may take x is x0 and x1 and x2. And this way you will obtain a forbidden sequence.
Okay.
Corollary 2. It's not possible for x and y that x is an element of y and y is an element of x. So please prove it. What would we obtain otherwise?
The infinite sequence.
Which one?
Y is an element of x is an element of y, and so on.
Of course. So no such situation as well. Okay. And now let's prove that these two sets for whatever A and B are not equal. This one and this one. These are distinct. Moreover, it is not possible to have either inclusion. Let's prove that this inclusion from the right to the left is not possible. Let's assume that this set is included into this. By the way, why aren't they equal? Does anybody have any idea?
Well, because by definition, the elements inside of them, like of one, does not belong to another.
But why? Maybe A equals this set and B equals this set and C equals B. Why not? So we have to analyze our assumption. Assume that this one is a subset of this one. What does it mean? When one set is a subset of another one, then every element of the first set is an element of the second one. What does it mean here in this situation?
Wait, if B is okay.
Let's consider B. B must be an element of this set.
Yes. So if B, yes. So that means it must equal either AB or BC.
So B is either this pair or this one. Is any of such statements possible?
Oh, because of the axiom of foundation.
Of course. That means that, you know, B is an element of the right-hand side. If B is an element of the right-hand side, B equals this set. That means that B is an element of B. And the same conclusion here. So we have either B an element of B or B is an element of B. Logically, that means that B is an element of B in any case. which is not possible according to our foundation axiom. So this one is not true. Is it clear?
Yes.
But of course, now we see that these sets are not equal. But maybe this set might be a subset of this one. Let's give an example if it is possible, or otherwise, let's prove that it isn't. It is possible that this set is a subset of this one. If it is, then what?
Every element
Then
from
Every element, and in particular this one, must belong to the right-hand side. What does it mean?
that it equal either A or B or C.
Of course. Interesting. And what can you say about these three statements in the disjunction?
We can say about the first one, so A is an element of A.
Of
so
course,
it's
the
not
first one is not possible.
Yeah, the second one is not possible too.
So that means that of these three, out of three possibilities, two are in fact impossible. That means that C equals this set. But no contradiction so far. On the other hand, we have not used all our assumptions. We have another one. BC is a subset, is an element of this set. What does it mean? That means that BC belongs to the right-hand side, or
BC is equal to A, or BC is equal to B, or BC is equal to C.
But this one is not possible, for in this case B is an element of B, and likewise here C is an element of C. These are not possible. So that means that from this implication, where at least two members are false, we obtain that A equals this one. So can we get a contradiction now, where A is an element of B, C, and C is an element of A, B?
Oh, yes, we can say that we can substitute A for BC, and then we get that there's the other.
And what of it?
So okay, B is, wait, no.
C is an element of A.
Oh, yes, yeah, and A is an element of C.
Element of C. So it is not possible. Why? Because such situation leads us to an infinite descending chain. It's not possible. So this is a contradiction. So neither inclusion is possible. For whatever ABC, these sets are independent. That is, neither is a subset of the other one. Is it clear?
Yes.
At the lecture, we introduced the following set builder notation. It is possible to take all x's from A which satisfy some condition phi, some predicate phi. Namely, this set satisfies the following obvious condition. Y is an element of this set when, if and only if,
It satisfies phi of x.
it satisfies phi, not of x, or y. That's y, by the way.
Yeah.
Y satisfies phi and y belongs to A. So it is possible to pick some elements from a set according to some property, to some predicate. Is this idea clear? Is it clear or not?
Yes.
This is widely known as a set builder notation. Okay. And now let's apply this idea to the following. I'll give you a natural language description of a set, and you are to translate it into our set builder notation. So in English, let's consider the set of all integer roots to the polynomial let it be, say, p of x. It is something scary. But for the best effect, let's rewrite it here. I mean, a psychological effect. Okay. All integer roots to this polynomial. How is it possible to define this set using the set builder notation? So please.
X set. Okay.
Let's rename them to n, as this one is x.
Oh yeah. Okay. N belongs to the set of integers.
We take all integers such that
They satisfy P of X.
what does it mean satisfy?
Oh,
P of
I mean,
x is a number function.
Yeah, yes, P of X
function.
equals 0.
P of n equals 0.
Oh, I'm sorry.
P of n equals 0. Just that. Just that. Is it clear?
Yes.
And B, all subsets of U which have exactly one element. What about subsets? What can you say? Do you remember the power set? The set of all subsets, the power set. Do you remember it from the lecture?
Yeah.
The set of all subsets of U. So X is an element of this set, the power of U, if and only if this exists by our axiom. When X is an element of the set of all subsets.
Well, if X is a subset of U.
Of course. So we may take all subsets and group them together. So how is it possible to describe the set of all subsets which have exactly one element? So please.
So N belonging to, N belonging to P of U.
So
Such that,
here we want to say that N has exactly one element. But can we do that without explicitly mentioning the number of elements or something like that? How many?
Maybe single tone.
Of course. We should say that N is a singleton, but how is it possible to say it? The singleton of what? The singleton of some set. Which one?
Of X.
Whatever, Y of X. Of some set A, whatever it be. So I want to say that N is a singleton of what set? Of whatever set. So we just pick up the elements, the subsets of U, which are singletons. This is the main and only idea here. Is it clear?
yes.
Yes.
But why do we need set construction principles, set construction axioms in general? Why isn't it possible just freely group together all elements that have something in common? Why don't we just group together all x's which satisfies phi? Isn't it natural? It is natural, but unfortunately it is contradictory. As the prominent Russell's paradox shows. Let's see it. At first, let's prove the following statement. There is no set A such that for every x, x is an element of A if and only if x is not an element of x. You know that according to the foundation axiom, no set is an element of itself. But now we want to group all the sets together. In this problem, let's don't assume the foundation axiom. So here, we don't assume the axiom of foundation. The fewer elements you have, the better you are, of course. The stronger your statements are. Let's prove that there is no such A. How is it possible to do so? What would be the first step in proving that some object is not possible?
Seems that it is.
Of course, of course. Assume that there exists such set A so that it contains as an element every set which is not an element of itself. So I have this property. In mathematics, you take quantifiers seriously. If it says for each x, that means for each x, whatever, not reasonable x, not x being not too strange, but every and each, every and each. So, I have it for each x. Which x would be interesting to consider? If I have it for each x.
The empty set, maybe.
The empty set, okay. Let's take the empty set for x. Let x be the empty set. Then I'll obtain the following. The empty set belongs to R if and only if the empty set does not belong to itself. By the way, is this right-hand side true or false?
False.
It's true.
True.
Yeah.
It is true, of course. The empty set is not an element of itself. So, the conclusion is as follows. The empty set must be an element of our R. No contradiction so far, but we need a contradiction. What are the interesting choices of R? Can you suggest so, please?
The singleton of the empty set.
The singleton of the empty set. Of course, the singleton of the empty set is not an element of the singleton of the empty set. That's true. And also we shall have that the singleton of the empty set is an element of R.
Maybe,
no problem here.
Maybe we can take the singleton of R for X.
The singleton of I is not an element of the singleton of R. Y, by the way. Okay, let's take the singleton of R. So we have that the singleton of R is an element of the set if and only if it is not an element of itself. But whether is it true or false, as the foundation axiom is not assumed here, so it is not quite clear whether it is true or false. It's not interesting.
And could you repeat why we don't assume foundation axiom?
We don't like it here.
Okay.
We want to use as few axioms as we can. This is a general general tendency of mathematics. The fewer axioms is the better. Okay. But what if we take just R itself as X? What if we substitute R for X? What would be the result?
There is a
Ladies and
contradiction.
gentlemen,
That the R is
R is
element
an
of R.
element of R if and only if R is... Here it is. Is this possible?
No.
Maybe no.
Is it possible that some statement is equivalent to its negation?
No.
No, of course it is not possible. It's not possible. Why? You see that if R indeed belongs to R, then it is not so, and we have a contradiction. If R does not belong to R, then it does. Another contradiction. So that's not possible. We have got a contradiction. While taking X, while taking R as X. So if it is for each X, then it is for R itself, which is not possible. We have got a contradiction. Is it clear?
Yes.
Sorry,
The
but
fact-
if we want to prove this fact, can we just say that x equal to r or not?
X, no. This is true for every x. I'm not proving that some x is equal to a. I'll take a as x. This is true for every set. This says that it is true for every set. This equivalence holds for every set. In particular, it must hold for I itself. Why not?
Okay, thank you. Understood.
This is our standard understanding of the universal quantifier. It's true for every x, not excluding I itself. And this statement gives rise to so-called Russell's paradox after Bertrand Russell, who was a pioneer of logic and set theory and so on. Russell's paradox. Why is it a paradox? For it is a provable statement. Ha! The paradox lies here naively. We can hope that it is possible to group together all sets which have something in common. What if we want to take all x's which are not elements of themselves? They are quite natural. So the empty set is not an element of itself, and of course every set we know is not an element of itself. But can we just group all such sets together? No, we can't. Otherwise, there is a contradiction. Another pioneer of logic, Gottlob Frege, you probably have not heard about him, or have you?
No.
Gottlob Frege had gone insane. He lost his sanity. He became mentally ill when he had got familiar with this paradox, for he hoped that it is possible to formalize all mathematics using this simple intuitive notion of set, when you can just pick all objects which has something in common, which have something in common, which satisfy some property, and declare that their multitude is a set. But it is not always possible. What is our remedy for this paradox? Of course, it is set construction rules, set construction principles. So this one is forbidden. We cannot just group all x's that satisfy phi together. We need to take them from some previously constructed set A. And finally, let's see another connected thing. Statement. There is no set of all sets. That is, it doesn't exist V such that for each x, x is an element of V. It's not possible to construct the set of all sets. It is immediately clear from the foundation axiom. Okay, with the axiom of foundation, it is immediate. Why? If there exists such V, then what? Dear students, please be active. Assume that there is a set of all sets.
Then V belongs to V.
Of course. Then, of course, V belongs to V, which brings us to a contradiction in view of the axiom of foundation. But what can we say without it?
Without it exists.
No, no way. No way. It is still possible to get a contradiction. Okay. Let's assume that our V exists, and let's consider which is constructed the following way. Let's take all elements of V which does not belong to itself. Now this is legal. This is perfectly legal. Why? Because it has constructed using our second set construction principle. We have just picked all elements from some A which satisfy some condition. This one is legal. Clearly, if X is an element of A, then X is not an element of X. Is it clear?
Yes.
Yes.
And vice versa. You know that every X belongs to V. We have assumed that V is a set of all sets. Do you agree?
Yes.
So, and then if X is not an element of X, then X is an element of V and it does not belong to X. So X must be an element of A. Why? Because you know that for each Y, Y belongs to the set of all X's from A, which satisfy phi, if and only if Y belongs to A and Y satisfies phi. So you see that X is an element of V, as every other set, and by assumption, it is not an element of X. Hence, it is an element of A. So this holds for every X. Hence, for each X, X is an element of A if and only if X is not an element of X. This is contradictive by our first statement that it is not possible to construct such A. Is it clear?
Yes.
And now our final problem due to the connectivity troubles. We started a little bit later than we had to. So please let's take no more than 5 minutes and prove our last. So let's solve our last problem. It is easier. It is not that abstract. So it is a kind of some rest. Okay. So do you remember what the set of all subsets is? When y is an element of this set, let's repeat. Y is an element of the power of x. This is read as the power set or just the power of x, or the power set of x. When y is an element of the power set. What is the power set? It is a set of all subsets. So
Then X is a subset of Y?
really, y is an element of the set of all subsets of x when? When y is what? When y is a subset, or isn't it? Dear students, let's don't be like the unhappy Gottlob Frege. Let's remain sane. It is easier. It's easier. Huh? What's the problem? This is by definition. P of x is just the set of all subsets, by definition.
So y belongs to some set?
Y belongs to the set of all subsets. It is not a sum set. It is the set, by definition, the set of all subsets of x, which is called in mathematics the power set of x, the set of all subsets. Y is an element of the set of all subsets if and only if y is a subset. What's the problem here?
No problem.
Which subsets does this set have? 1, 2, 3. Let's list them.
A singleton of 1.
The singleton of 1. What else?
And the 2 and the 3.
Are these the only subsets?
Oh, and maybe an empty set.
So these are the only subsets.
No, the set.
Oh.
What else?
1,
set
2.
1, 2, 1, 3, 2, 3, and 1, 2, 3.
1, 3.
2, 3.
And what else?
1, 2, 3.
In general, you know that for every x, the empty set is a subset of x. Hence, for every x, the empty set is an element of P of x. And for every x, x is a subset of x. Hence, x is an element of P of x. So these two are necessary. Okay, how many of them do you have?
A lot.
Can you count them?
7?
8.
8.
8.
Yeah.
So it's the
Eight.
power of...
This is the power of 2, of course, 2 to the power 3, and it is not a coincidence.
3 elements.
Of course, three element set has exactly 8 subsets. And what's even more interesting is that you may depict them in the following meaningful way. Let's draw a cube. Let's draw a cube. Can we draw a cube? A cube, no. Mm-hmm. So is it, does it look like a cube?
Yes.
Okay, and now let's somehow mark the vertices. No. 1, 3. 1, 2. 2, 3. 1, 2, 3. What is the main idea here? The empty set is
Coordinates.
the subset of the singleton, of this singleton, and of this singleton. And there is no set between the empty set and this one. The singleton of 1 is a subset of this one and this one. And likewise for the other singletons. Is it clear?
Yes.
By the way, I can encode the vertices of the cube in the other way. I may put them into correspondence to binary words of length 3 by the following principle: 0, 0, 0, 1, 0, 0, 0, 1, 0, and here, so please.
0, 0, 1.
And here.
0, 1, 1.
And here.
1, 1, 0.
This point 1, 3.
1,
1,
0,
0,
1.
1.
And the last point.
1, 1, 1.
Can you see the idea?
No.
No. This is but if you can't see the idea, how is it possible for you to predict, to correctly predict our correspondence? Why we put this one into correspondence to this one? Because this word has 0 at the first position and 1s at the second and the third position. And this set has exactly 2 and 3 as its elements. So we have 1 at the i's position, if and only if I is an element of our subset. For example, for the empty subset, we have all zeros. Why? Because neither 1, nor 2, nor 3 is an element. Here we have that 1 and 2 are not elements of this set, but 3 is an element. Is it clear or not?
Yes.
This.
You may encode your subset of a finite set by a binary word where you have 1 at the i's position if and only if I is an element of your subset. Of course, you have 2 to power n or 2 power 3 such words, and likewise you have 2 to power 3 subsets. We shall prove it formally later. And now, as our final example, let's construct the graph, the inclusion graph, or the Boolean cube for in dimension 2 for subsets of 2-element set. How many subsets do we have?
Four.
4 subsets. The empty subset is the least one, and we have 2 singletons. Of course, we have an arrow here, but it might be restored from these 2. And also, you may put this into correspondence with the words. Is it clear?
Yes.
Any questions, dear students?
No.
No questions at all. So, please give me some feedback. Is anything clear?
Mostly.
Clear? Mostly. So, but not everything.
We just need some time for everything to be understood.
You need some time to digest all these things. Of course, of course. And doing your homework, which I'll post probably tomorrow, is the best way to do so, to grasp all these things. Thank you.
Thank you. Bye.
Dear
Thank you very
students.
much.
Thank
Goodbye,
you.
dear
Goodbye.
students.
Goodbye.
Don't
Goodbye.
hesitate to ask your questions in our group if you have any. Thank you. Thank you, dear students. Please do not postpone asking. Asking is very important. Don't accumulate your questions. Spill them. Okay. Thank you.
Fine.
Goodbye.
Thank you. Bye.
Goodbye, everyone.
Goodbye, dear students.